Special thanks to all the organizers who have brought us to this place where we can focus on cryo-EM for 2 days. And welcome to this session, which has a methodological focus. And it's a pleasure to introduce the first speaker, Chris Russo from MRC LMB in Cambridge. And until now, his title has remained shrouded in secrecy, but he's going to talk about determining and overcoming physical limits in electron cryomicroscopy. Chris.
Wasn't intentionally shrouded in mystery, but it's accidentally through my own fault. Anyhow, thank you very much for the invitation to be here. It's a great pleasure to speak with this audience, actually, and it's what I think is going to be an excellent meeting. So I'm going to talk about a few things today, but I'm going to start. I'm going to talk about studying physical limits in biology, but I'm going to start with an actual example as to why I think this is interesting and sort of how sometimes studying one thing allows you to figure out a way to deal with another problem, completely serendipitously, really. So this isn't going to be your sort of average overview talk. I'm going to try and get at least one idea across to you. It's a fairly difficult idea, but I think I'm going to try and present that first. And then I'm going to sort of back out and look at a more sort of overall view of what I think the physical limitations in cryo-EM are and how we're trying to understand each of them. So this is a virus, obviously. And I've just taken a micrograph from the Empire database. This was deposited quite recently. It's a high-resolution structure of the P22 virus from Ma Chu's group. And you can see it's pretty big. And traditionally in EM, when you go to sort of introductory talks, the first thing everybody tells you is that an EM image is a transmission micrograph, i.e. it's a projection of some sort of density. If you're new to the field, people call this electron density, but as was mentioned earlier already, it's not. It's the total Coulombic scattering potential of these atoms. But anyway, you shoot the electron beam through this specimen and you end up with a projection image. And if you don't remember anything at all from this talk today, remember this thing. This is wrong. It's not true. Does this work? Sorry, there we go. Wrong. Electron micrographs are not projection images. And they're not projection images for this reason. This is the Ewald sphere. I'm surely pronouncing it not very well. And Paul Ewald was a German physicist who eventually ended up in the States. But anyway, he was working on X-ray diffraction in crystals and came up with this very elegant description that basically is just telling you Bragg's law in some sense. This is the conservation of energy and momentum in reciprocal space. And he said that the energy of the elastically scattered electrons is conserved, so therefore their wavelength is going to be uniform and describe a sphere in reciprocal space. So any electron that gets scattered out in some diffracting beam has to obey this property or fulfill this criterion called, which we commonly think of as Bragg's law. So I think, but this is a problem in EM because even though we assume that our images are projections and we do all of our reconstruction with this, our projections, and we do all of our reconstructions under this assumption, they're actually not because of this physical phenomenon. So I'm going to try and explain this to you and how we think we have a way of dealing with this now that we didn't have before, but it really came out of studying a completely different problem in the field. Now this Ewald sphere curvature has been known about for a long time, even in EM, and has been addressed by various authors in the past. Probably most notably by David de Rosier, who sort of did a nice mathematical description of it in 2000, and then later on with Nico, he implemented a couple of different schemes to try and correct for the curvature of the Ewald sphere in electron micrographs. And in the method I'm going to show you today is actually quite similar to one of the ones that was proposed here, but it has a few more details in it. And even as recently as last year, Ken Downing and Bob Glazer did a paper where they simulated the effect of the Ewald sphere on high-resolution images. to show that this actually, this is a significant effect, and that needs to be dealt with, really. But so what did we come up with? Well, we came up with this idea from staring at micrographs like this. So this is a micrograph of 10 nanometer gold particles in ice, imaged just as you would any other protein particle. Standard low dose sort of conditions, 300 keV, it's at 80 Kelvin. And we took lots and lots of images of these particles because we were trying to understand charging and movement of specimen and radiation damage. And these turn out to be very useful sort of little test specimen because we know them so well and they have such good contrast. But one thing we did was take a defocus series. So I'm just going to let this play for a moment. I don't know how many of you have done this, but you've probably taken images at different defoci, in various conditions. So this is going up from 0, basically in focus, or slightly defocused, to minus 10 microns of defocus. And you can see, well, first of all, the particles start to look fringy. These are Fresnel fringes coming off of the individual gold particles, but there are these other things here. See these white dots? Does anybody know what these are? You can shout it out, it's okay. Some diffracting beams, right? This is Bragg's law. We're looking at Bragg's law. You can look right at it. The gold particle is a crystal. It has a spacing, or at least one spacing, that's at 2.1 angstroms. And when that lattice happens to be aligned nicely along the beam, you get a good diffraction from it. It goes out both directions and creates a bright contrast in the image because you've shifted the phase of that wave. And so we're looking at the phase contrast between the scattered and unscattered electrons at that position. And so these beams are coming right out of the particles, and it's exactly the same thing for a protein particle. When you put your electron beam through your protein specimen, the electrons are diffracted out, and the further in defocus you go, the more delocalized those diffracted electrons get, and those are the things that are actually creating the contrast in your micrographs. So this is just a montage of what I just showed you in movie form. So at 2 microns defocus, a 2.1 angstrom particle has a delocalized lattice out here. And there it is. There's been nothing special done to this micrograph. You're just looking at the micrograph. You can see the 2.1 angstrom 2.1 angstrom resolution lattice right in the micrograph, right? And as you go to 4 microns, you can see it here. 6 microns, 8 microns, right? So the further you go, the further it's delocalized out. Yeah? Okay, so what does this have to do with Ewald sphere and all this other stuff? Well, I promise I'm going to try and pull all this together. So what do we do normally to a micrograph with defocus? We do CTF correction. Well, what is that? Well, that's from this very famous seminal paper from Eriksson and Klug, where they described the delocalization and basically the transfer of information from an electron micrograph to, or from the particle to the electron micrograph as a function of defocus. And this is where the idea of CTF correction came from, that you could process this image after you had taken it and then re-put all of these Fourier components back in the correct positions. So in other words, in that previous image I showed you, those 2 angstrom lattice is way outside the particle, right? They've completely delocalized because we're looking at a focal plane that's far away from the specimen. And CTF correction takes that information and puts it back right on the particle, right? And that's what we're doing when we do CTF correction. So that idea is sort of diagrammed here. So you have a specimen here, and it has beams being diffracted out from it, right? And your lens creates this diffraction plane here, where the Fourier components are then separated from each other. And what we actually look at when we look at an image is not the in-focus version, but some under-focused version, because it gives us some contrast. And in that under-focused image, the high-resolution information has all been delocalized from the actual particle. It gets spread out radially by Bragg's law. And the further away you go in focus, the further it gets spread out, right? And that you can see here. So this is just a raw micrograph of one of these gold particles in ice, low dose, just as we would image. And here are the 2 angstrom lattice reflections. So you can imagine if this were a ribosome or a virus, then all of the high resolution stuff that you're really after is actually out here at this particular defocus. And the more in defocus you go, the further delocalized it is. And what we do when we do CTF correction is to take that delocalized information and fold it back in. That's what this CTF multiplication in Fourier space actually does. So I can show that to you visually here. So here's the original image, and then here is CTF correction in the traditional way. Multiplying in Fourier space takes this delocalized information as a function of spatial frequency and folds it back into the primary image. But there's a problem here, and I don't know if you've noticed it yet in the micrograph. The arrows help. Can you see that? Everybody see a little bit of fringes there? The trouble is this CTF correction takes this sideband, if you will, of high resolution information and flips it over here, but it also flips it over here. Everything gets flipped by that amount, by multiplication in Fourier space. So although CTF correction is very good because it takes a band from here and flips it over here, and takes this band from here and flips it over here, it also takes half of the power here and flips it outside. And you throw this away, right? So you're effectively throwing away half of your signal in every image when you CTF correct it. And we have to do this in order to re-put all of the high-resolution components back into the particle in the correct position so that we can then go and do reconstruction and all the rest of it. So what if we didn't do that? Well, now we're back to Ewald sphere. So sorry, there's one more idea I have to introduce here. So and the problem with traditional CTF correction is it takes both of these sidebands in both directions and puts them back together right in the same place and overlaps them with each other. However, they're not the same because they are sampling different points on the Ewald sphere. And therefore, putting these two together actually entangles them such that there's no way to determine whether they were on one side or the other. And this is why the image is not actually a projection. This is the sort of Fourier argument for those who like to think in Fourier space. But the other way to think about it is you've taken this beam here, which just got diffracted out by Bragg's law from the chunk of gold, and you put it in over here. But this diffracted beam is not exactly the same as this one. So when you put them back together in the same place with the same weighting, you actually mix up a certain amount of the information. And that leads to a loss of high-resolution information. And that's why Ewald sphere curvature is important. But as you can see, probably where I'm going now, you don't have to put them both back in the same place at the same time. You can do them one at a time. So if the last one was called CTF-R, which is the regular one, the Ericsson and Klug style, where you multiply by a real function in Fourier space, then this is a slightly more complicated version of that. So now we use a complex function in Fourier space, which then allows us to take one sideband and put it in the correct position entirely. All right? So here's CTF-P. So now we've taken this information here and folded it right onto the particle. And now there's absolutely no loss. We haven't kicked any information back out like we do in regular CTF correction. We've put it all in the right place. And we can put it correctly in Fourier space according to the curvature of the Ewald sphere, which we know just based on the wavelength of the electron. And then this band gets folded out. So now the only thing we need to do is actually mask off this image of the particle and then use this in our reconstruction. But half the information is still gone here, right? We want to keep this too. So you just do it twice. So now you do CTF-Q to take the information that used to be here, fold it over and put it correctly on the particle, and that throws away this sideband. And now you can mask this off, and now you have, and you can put it in the correct place in Fourier space according to the curvature of the Ewald sphere for that diffracted beam. right? So I think that it's a very sort of simple idea, which just came from staring at lots of images of gold particles where you saw these beautiful diffracted beams going out from each particle. And it means that we can treat the curvature of the Ewald sphere absolutely, pretty much perfectly, post in computation. But the thing you have to give up on is this notion of a projection. It's not a projection. Each micrograph is not a projection of the image. It's actually this weird sort of delocalized version of your particle, which smears out as a function of position as you go to higher and higher defocus. Okay, so that's the idea. Does it work? Yes, it works. So we just took that data set from Empire, and Shores and his postdoc Takanori very kindly implemented this in the latest beta version of Relion to try it out. And you can see, so the published data set was at roughly 3 angstroms resolution. So if you take the two sidebands and do this processing as I've showed you, and put them in the correct direction, you get an improvement in resolution. If you put them in opposite, the wrong way around on the Ewald sphere, it gets worse. Now this actually gives you another interesting benefit, and that's actually a symmetry breaking, right? So the Ewald sphere curves in one particular direction, not the other one. And that's also very interesting. And so you may know of this problem of handedness in structures, right? The reason we don't know the absolute hand of a structure calculated by traditional methods in cryo-EM is because we've been assuming that these things are always projections. So how can you tell the projection of a handed molecule is one way or the other? You can't. There's a symmetry problem there. But this Ewald sphere is not symmetric. It breaks the symmetry. And therefore, when you process the data in this way, you actually get the handedness for free, right? Because these terms that you're populating Fourier space with when you do the reconstruction are all going in the correct position in Fourier space, and they're doing so asymmetrically. So if you process data in this way, you will get the hand right automatically. And conversely, if you wanted to turn this into a validation test, is my hand correct? You could do exactly this. Just process it with the Ewald sphere in the right direction and the wrong direction. And if the resolution gets worse in the direction you think, you've probably got it wrong. So you can easily turn this into a validation test if you wanted to. Okay, so that's it for my Ewald sphere spiel. The details you can read about in the paper, which we recently published about it. But the idea is that you can do exact correction for the curvature in every micrograph. So the only thing you have to do, actually, so there is a catch. You have to collect data at defocus. So if there's no defocus in your micrograph, you've overlapped all of these Fourier components, and there's no way to tease them back out again. And there's no way to properly correct for the curvature of the Ewald sphere. So in order to do this properly, you have to just make sure that you've gone to enough defocus that the high resolution frequencies you're interested in are sufficiently delocalized that you can put them back in individually, right? And if you do this, then we can do sort of perfect Ewald sphere correction. And this removes one of the things that we thought was going to be a physical limit to going to lower energy in EM. And that is to say, as you go to lower energy, the wavelength goes down, so then the Ewald sphere gets more and more curved. So this effect gets worse and worse the lower the energy you work at. So, but I think if we process data in this way, we won't have that problem. Okay, how far can cryo-EM go? So we're still working on this, but ultimately we think we're going to try and understand all of the sort of physical phenomenon that limit us in cryo-EM, and then understand exactly how far we could go. And sort of our rough idea right now, which is not really new, but it's getting more and more accurate since Richard's prediction many years ago, is that we should be able to take a handful of micrographs, say 50 micrographs of a ribosome like this, and get a 3 angstrom structure, no problem, right? And we're not near this yet. So I think there's a lot of room to go. And so why do I think that? And just as importantly, how do we get there? All right, so this is why I think it. These are B-factor plots we have lots of crystallographers in the room, so I'm sure they know and love the B factor well. We sort of use them a bit crudely in EM, quite honestly. I mean, these aren't real Debye-Waller, temperature parameters, but they are good fits to the sort of exponential behavior of the movement of these molecules. But anyway, if you dig into many of the high-resolution structures that have been published over the last few years, you'll occasionally find a nice plot that looks like this, which is the B factor applied to the final reconstruction as a function of dose in these movies that we can now collect. And I've stared at these plots an awful lot and thought about them an awful lot. And ultimately, they're extraordinarily frustrating or sort of dissatisfying. So if you're not annoyed by these plots, then I think you should think about them some more. These are disturbing, right? Because what this says is that the beginning, when you first turn on the beam, we throw away all that information, chuck away all the high frequency stuff when the beam is first on, when the molecules are not damaged. And then only start using the information after they've been cooked, right? And then keep on going as far as you can when you've really cooked them, and use all of that to do your reconstruction. But the first bit that's totally undamaged, just throw that all away. So this is deeply disturbing, right? Like bonkers. Okay, so what do we think is going on here? Well, this is our grand scheme, as it were, rough grand scheme. We're trying to put numbers on all these curves, but basically we're trying to understand all the things that contribute to the B factor as a function of electron fluence in a high-resolution cryo-EM micrograph. And this is what we've come up with. So I'm basically giving you the answer before I've actually shown you any of the data, which is a bit of a bad idea, but anyway. And it's currently unpublished, although Richard did show it in Stockholm, so I'm not sure it really counts as unpublished anymore, but anyway. Here is what we think should be if our micrographs were sort of perfect, right? This is the radiation damage limit. We think, the damage to the molecules should be progressive, and we have a rough idea of what this slope should be based on lots of electron diffraction experiments and even X-ray diffraction experiments, which tell us a lot about radiation damage physics. But what we actually see is this sort of terrible thing at the beginning, and then it sort of peters off and eventually has a slope which approximates what we see in diffraction experiments. But we need to know these in more detail as well. Anyway, there is a phenomenon that's of interest, which is the movement of water molecules, which I'm going to mention briefly, which we think is happening continuously as the beam is irradiating the specimen. So the water is not a solid. It's actually moving. It's pseudo-diffusing around, and this gives you a B factor because it's pushing on the molecules, making them move. There are fluctuations in charge on the specimen. We've recently started measuring these, and we found out that they weren't nearly as bad as we thought they were. But they are continuous and happen almost instantaneously when you turn on the beam. And then there's movement of the specimen. And you can tell that one's important because I put it in bold. And we think actually that is the primary component in the loss of information in all of these micrographs that we take. And then finally, there's buildup of charge in the specimen, which is also could be extraordinarily important because this lenses the beam and causes lots of problems. But as it turns out, it happens extraordinarily fast. So we've been able to measure this recently as well. And I'll talk very briefly about that. So we think the sum of all of these is why these curves look the way they do. And if we can sort these out, then we may actually reach the full potential of cryo-EM. Okay, let's start with the first one, water movement. I'm not going to go into any detail at all. You can look at this reference. So this is also an astonishing result. The first time I sort of read it and understood what this meant. But what it means is that for every electron that goes through the specimen, you give a certain kick of energy to the water molecules in the specimen. And those water molecules start moving around. And that movement actually causes movement of the proteins. So it's just like Brownian movement of a dust particle in a glass of water. And you can describe it with the same sort of physics and figure out how much a particle moves because of this. And that's this part of the curve here, which happens continuously as you're irradiating the specimen, as far as we know. Okay, next, charge fluctuations. So what is this? So the electron comes down on the specimen, very high energy. It can very easily kick out other electrons. And in kicking out those other electrons, it leaves behind positive charge. Ice is an insulator, charge can't just go flying inside. And then in kicking out those other electrons, they can actually land on other regions of the specimen and charge them up. And you get this whole sort of dancing phenomenon of charge that's happening all the time in your images. And you can see this here. So this is called the bee swarm effect. It's been known about in EM for forever. The theory was worked out by Curtis and Ferrier in Cambridge, actually back in the late 60s. But you can see it very nicely in these sort of movies. And this is a 100-frame movie of 2 electrons per angstrom squared. So what this should tell you is this is happening very, very fast, right? So these are, 0.02 electrons per angstrom squared per image. So this happens extraordinarily quickly, and we figured out how to quantify it. And the way we figured out how to quantify it was actually that image I showed you previously, these gold particles. So if you look at these individual images of the lattice, as I showed you earlier, you can measure the power in each of these. And you can measure the power as a function of defocus. And because the further you go out into focus, the more a charge on the specimen affects the angle of the electron wave coming out, the more these should be blurred out, right? If charging were causing a problem. And we thought this was going to be a big problem, actually. And then we managed to do the measurement and realized that it actually isn't a big problem. So even at 10 microns of defocus, you only lose maybe, 10 or 15% of the power in the image, right? So even all the way at 10 microns of defocus, you can see the 2 angstrom lattice, no problem, right? And so what this means is that this phenomenon, while always present, is actually very small. And we don't need to worry about it too much as long as you set the imaging conditions correctly. And so you can also extrapolate this as a function of energy and see how much this is going to affect you as you go to lower energy, because going to lower energy is a problem for specimens that charge. Delta E over E is roughly how these things scale, right? So bigger charge, lower energy beam for the same charge, you're going to have a worse problem. Okay, what's next? Movement of the specimen. Oh, I'm totally running low on time, so I have to skip. Movement of the specimen. I'm going to skip most of this. Most of you have seen these before. This is the substrates that we came up with that actually reduce movement of the specimen by about a factor of 50. I have one of them here. So there's crystallographers in the audience, so let's just sort of do a fun diffraction experiment, right? Bragg's law. And if I told you the wavelength here was 532, you could tell me the spacing between the holes, right? Anyway, that's them. And the interesting thing is that they reduce the movement of the specimen support by a factor of 50. And this reduces the movement of the specimen itself by roughly a factor of 2 or even more, depending on how bad you've done with regular carbon grids. Right. And lots of people have started to use these now. We published how to make them, and then we also commercialized them so that you can just buy them, and there have been a lot of recent structures on them. So I won't say any more about that. But even so, there still is quite a lot of residual movement right at the beginning of irradiation. And we think that this is actually the movement of the ice within each hole. The hole is no longer moving on a gold grid, but the ice still is, and that's the part we have to deal with yet. And then finally, this charge-up phenomenon. This is the quote-unquote Berryman effect, named after John Berryman, who was the first one to notice this in a very early low-dose system at the lab. It was eventually published. And basically, it allows you to see the buildup of charge on the specimen right at the beginning of irradiation. And so we can then sort of quantify this, roughly. And the interesting result here is that the charge builds up on the specimen in 10 to the minus 3 electrons per angstrom squared. Certainly by 10 to the minus 4, it's already built up. So that's why this curve here is so steep. So this still may be an issue, but we think it's happening so fast that if it's reaching some sort of steady equilibrium state, then we won't need to worry about it as much as we once thought we did. Okay. So if you'll indulge me in one last slide, this is sort of what we think the future of cryo-EM might hold in a few years. we're hoping that there's going to be a low-cost instrument that's roughly 100 kV in energy that could be in any biology department or lab. And by low cost, I mean, well under 500,000 in whichever currency units you like to use. And this will allow you to do, sort of 4 angstrom structures easily, and also allow you to very rapidly screen your specimen and understand how good they are before you go to a high-end, state-of-the-art equipped facility like Diamond or other centers around the world. And then finally, there's going to be an entirely different type of microscope that's dedicated to tomography. And I haven't talked at all about this, but we don't see any reason why you couldn't do, say, 1,000 tomograms per day. We could do 1,000 single particle cryo-EM micrographs per day. So I don't see any reason, fundamental physical reason, why you couldn't do this for tomography as well. Okay, I'm out of time, so I'll stop there and thank the people at the LMB. So this is my little group here. This is Katerina and Matthew. And these are other sort of engineering master students and other people who have rotated through the lab. But these are the folks who are doing lots of projects, most of which I didn't actually show today. And these are all the people at the LMB who have contributed to various parts of this work in the past and in current times. Some of who are, I'm sure, in the audience. And the LMB is a great place to be and to work on, sort of hard problems at the interface between physics and biology. So if you're interested, please get in touch. And with that, I'll stop.
Chris, thanks so much. I'm sure Chris is happy to take some questions.
Thank you. Hi, Chris. I have a question about the first part of your talk. Am I right to think that you could use the position of the diffraction spots from the gold bits to determine the absolute value of the focus? And could that be a useful detection method for tomography, for instance, to detect the CTF?
Yes, so we have already worked on this quite a bit to see how accurate you could determine the defocus based on the diffraction patterns, and it's quite accurate. Unfortunately, the particles do move, so not all of them, even if they start out diffracting, by the end of a tomogram or the end of an image, they may have moved off plane so that they no longer have the lattice, on the zone axis. And that means that you can't use the lattice to actually determine the position of the diffracted beam. And then that reduces the accuracy by about a factor of 10. But for a really good particle like the one I showed, you can do it better than 50 angstroms, I would say.
Chris, great talk. Just one suggestion first. I think this idea that we shouldn't call them projection anymore, you got to give it a short name so that it sticks with the community. And it's you choose.
Oh, we need a name. Okay. I'm not very good at that.
The important question I wanted to ask is, so we need now to go back to defocusing for this delocalized information.
Yep.
Is this going to kill the faceplate business, or is it useful to still use the faceplate and you can apply the same Ewald sphere correction by slightly under focusing?
So ultimately we need to do the experiment to find out, I think is the short answer to the question. The trouble is, in a perfect phase plate, if we had a perfect phase plate that, that gave you an exact 90-degree shift at all spatial frequencies, then you would always work at zero defocus, right? But unfortunately, we don't have that yet. But until we have that, but you still wouldn't be able to do Ewald sphere correction. But if you wanted to do Ewald sphere correction with a perfect phase plate or even an imperfect phase plate in this way, you can go to defocus and then use it in the same way. So you just have a sine instead of a cosine. All the operations are the same, basically. So you can do everything that you did here on phase plate data. But you're not going to have as big of an effect of the phase plate itself once you go to defocus, right? Because you've damped down these lower spatial frequency components that you were after with the phase plate in the first place. So, but it's going to be a trade-off, and there'll be sort of a in-between. So that's why I say I think you need to do the experiment to find out how much you're really going to gain.
Hey, I was wondering if the conclusion we should be drawing from the charge build-up thing, the lensing, is that you don't worry about it because it's only a few, like a bit of dose at the beginning, or do you think that you could either use paraxial illumination? Has anyone tested that? Or would you do like a little low-dose pre-exposure somehow with like a semi-transparent shutter?
Well, it's convenient that our chair is the world's expert on paraxial illumination, and I think he can actually answer your question better than me. But certainly you could use a paraxial illuminator to neutralize a certain amount of that buildup of charge. I think you're not going to get rid of the charge completely, but it's very interesting to think about how you could configure that in a way that would completely eliminate any sort of charging phenomenon there. Yeah, I don't know. But I think in a lot of situations, the buildup is so fast that it's less worrisome than you might think, right? And another way to look at this is in terms of shifting defocus. How much is your defocus varying as a function of dose? So in some conditions, when if your specimen is charging very badly, you'll see big shifts in defocus. But if it's not, then they shouldn't be shifting much at all. Well, I think the goniometer is the key thing here. The detectors are fast now and will be even much faster in the next generation. So there'll be no problem collecting enough electrons to give you 1,000 tomograms a day. So now you just have to tilt the specimen in a way that you preserve the high resolution information in each one of those frames. So how do you do that? I don't know how to do that.
Okay, one last question.
Thank you for the great talk. My question is regarding the first part of it. Does it mean that we will have a sweet spot in terms of defocus for a given wavelength and given size of particle?
Yes. There's a plot in the paper. I have a slide. Yeah. So this is the trade-off between sort of defocus and particle diameter. So let's say you wanted to keep everything from 4 angstroms on well separated in the two side bands. Then for 300 kV, if your particle diameter is only 100 angstroms, you don't need much defocus at all. It's maybe 2 or 3 microns or something. So for small particles, you don't need much defocus. But of course, small particles don't suffer as bad from Ewald sphere curvature because they're not as thick. For a large particle like a virus, ideally you would be at quite high defocus, say 10 microns of defocus. But you should still see an effect even if you're not at 10 microns of defocus, because the Ewald sphere curvature affects the images of large particles more. And then this is the energy scaling version of that. So this is, sorry, it's not labeled, but 300 kV versus 100 kV. And you can see at 100 kV, you don't need to defocus much at all, actually, because the Ewald sphere is much more curved, and the beams diffract out at higher angles, so then you can delocalize them with much less defocus. So, but if you look in the publication, we address the trade-offs between these two things.
Okay, in the interest of time, we have to stop and maybe give Chris a hand.
Thank you.
But